Resonance in AC circuits is just an electrical analog of the resonance in mechanical systems. Since we haven't covered this topic in the last semester, it's a good idea to give an overview of this phenomenon. So what we have in here is essentially an oscillator. This is a mass attached to a spring, but we know that it's going to oscillate with some certain frequency. Whatever it is, it's not that important. So that's called the natural frequency of oscillation. So we know that in physics, these oscillations are everywhere around us. So essentially every system which is slightly displaced from stable equilibrium positions, they are going to oscillate. In any case, we apply an external force to that system. So this force is in addition to the spring force in here, right? Just keep this in mind. It's an external force, so it's something that we can adjust. But this force is periodic in time, and it just depends on time periodically. So I'm just taking this sinusoidal dependence on time. What is important in here is that sometimes we pull the mass and sometimes we push. So the force therefore changes direction, and it changes direction periodically. In any case, so the physics of this kind of a system can be quite rich, but we are interested in only this resonance condition. So the question that we ask is general, and of course I'm going to give a very general answer. So how does the object respond to that force? So what happens is that, what it appears is that the largest response of the system to that driving force is obtained when somehow these two frequencies match. So when the frequency of the driving force is equal to the natural frequency of the oscillation, somehow this oscillator display the largest possible response. And we are going to understand why, but the simple answer is that somehow when the exact resonance condition is satisfied, the force and the motion of this object in here become always in phase with each other. So as a result, it appears that whenever the object is moving towards right, for example, the force happens to be also pointing towards right, and vice versa. So when the directions have changed, we are going to have the same kind of a situation. So what does that mean? This essentially means that this force always gives energy to the oscillator. So therefore, the energy of the oscillator continuously increases. Right? So the situation is something like that. So I have drawn as an example, of course, to be able to solve this system, you have to write down the equations and solve them, but we are not doing this. So as a result, in here, what I'm doing in plotting in here is I'm plotting the velocity versus time graph for an oscillator, assuming that there is no external force. In addition that I'm plotting the force in here. So when the frequencies match up, so this is the case in here, when both of these frequencies match up, and I have also shown the case where the phase difference between these two oscillations to be equal to zero. So they are always in phase. So that means when the force is positive, the velocity is positive. When the force is negative, the velocity is negative, and so on. So this never changes. So as a result, for this kind of a situation, the power that the force gives to the oscillator, that's essentially the energy given by this external agent to the oscillator, this is always positive, right? Which means the oscillator somehow is always given an energy. So by using this fact, we can then plot, for example, how the position is going to look like. So I'm just going to draw a graph in here, in here, so showing the typical behavior of the position. So it's basically an oscillation with the same frequency, but the oscillation amplitude is going to increase continuously. So there is going to be a steady increase. And it appears that this is actually an exponential increase, but that's not that relevant in here. right? So that means, so the amplitude increases indefinitely, but of course there are some approximations that we have made, especially probably we haven't mentioned about this friction thing. So if there's friction, for example, this is going to be bounded eventually. So as a result, this is going to come down. So you might ask what happens if the force and the velocity, they are out of phase. So, I mean, it might actually happen that accidentally the force and the velocity are in opposite directions all the time. This might happen too. In that case, the power is always negative. But in this kind of a motion, the amplitude of the motion is going to continuously decrease. But whenever it becomes zero, it will start increasing again. So as a result, eventually we are going to reach to that resonance condition too. So at this point, right, when the frequencies are the same, somehow, therefore, there is a continuous pumping of energy to the oscillator, and so therefore the oscillator shows a very high response. So what happens if the frequencies mismatch? So I'm just showing this situation in here when the frequency of the force, the driving force, is slightly bigger than the frequency of the velocity, frequency of the natural oscillation, basically. So you can see that at least at the initial times, the force and the velocity are almost in phase with each other. So, I mean, there are some times in here, small times, where the velocity is positive, but the force is negative and things like that, but these are very short times, so just forget about these. So you can see that at the initial times they are more or less in phase, so therefore the power is more or less positive in here, more or less. So let me just write this thing down in here. But eventually there comes a point where they become out of phase. So as a result, whenever the velocity is, let's say, towards left, the force is towards right. So there comes a time where the power is therefore negative. So for this kind of a situation, therefore, the position or the amplitude of the oscillation initially increases and then it starts decreasing, right? So there's a certain time where energy is given to the oscillator by this external force, and there's another time where the energy is taken away. So if the force, if these two frequencies are significantly different from each other, this beat time in here is very short. So as a result, the oscillator is going to do a very complicated motion, but we will see that the amplitude cannot increase indefinitely. But if the frequencies are very close to each other, then we are going to have a situation which is very close to the resonance. So let's just do it like this. So I'm just going to talk about this kind of a situation. So position is plotted in here. So the position is going to basically look like that, and then perhaps it's going to decrease and then increase again. Perhaps there might be a friction elsewhere also in here. So let's consider about this maximum displacement that you achieve. So basically, this is the largest displacement that you might have for this kind of a motion. You can expect that this maximum displacement is proportional to the amplitude of the force. So let's just take the ratio of this thing. So as a result, this ratio somehow gives us the strength of the resonance in a way. So what we are saying in here is that if I plot this quantity, for example, as a function of frequency, there is this natural frequency in here. So what happens is that at the resonance frequency, this is infinite. If there is no friction, if this quantity is infinite, so at the resonance somehow there is no maximum point in here. So as a result, the amplitude starts continues increasing. So let's say it like this: no friction. If there is no friction, there will be an extremely large response in there. So if this is infinite, then it's not possible to plot all the other things. But if there is friction, of course, this is going to be bounded. So in such a case, we are going to get a very nice curve like that. So that's called a resonance curve. So this is the situation where, let's say it like this, the no friction case is the mid curve in here. Let's forget about the situation. That's not that important, right? So let's say it like this. This is small friction, in which case we are going to get a very narrow curve. But if the friction is large, it appears that the peak has decreased, so therefore the response of the system is somehow smaller, but it just responds in a very large region. So as for the large friction. Okay. Usually we measure the width of this thing by the range of frequency in here, and the quality factor is usually is defined as the ratio of the frequency, the resonance frequency, with the width. So that's called the quality factor. Quality factor basically tells us how sharp that resonance curve is. So it's an indication of how good a resonance condition is satisfied. So in that case, to be able to achieve real resonance, of course, you have to be very close to the frequency in here. And usually this is what you desire, especially for electronic circuits, for example. If you want to just isolate one single frequency, then that's the condition that you would like to achieve. And this is usually achieved for very small frictions, so sufficiently small frictions, you will get this. So when the friction goes to zero, this peak basically becomes very sharp, and the peak point of the peak actually goes to infinity. All right, so we also essentially see the same thing for the electronic circuits. So somehow in that case, the response is the current divided by the, I don't know, the input EMF, for example. In that case, we also have this kind of a resonance curve for the response of an electric system.